If you've ever opened up a synthesizer in your DAW, you've probably heard this sound before. Most synthesizers contain at least 3 waveforms: the saw, the square, the sine, and the triangle. Today I'm going to explain to you why these particular waveforms are so important to all the music all around us, and why the synth wizards decided on these waveforms as the basic shapes, and not some other ones. Like, look at this looks really... Well, to get started, I will first introduce you to my good pal, the sine wave. The sine wave is a simple waveform. It's nice and round and very smooth. The sine wave is a very special waveform because it's the only waveform that consists of a single frequency, while all other possible sounds other than complete silence consists of more frequencies at the same time. Here, look. This is a visualizer that tells us which frequencies are currently happening inside of the sound we're hearing. This is a piano, and this is what a sine wave looks like. You see how the piano has a bunch of frequencies at the same time? This means a few things actually. One of these things is that yes, the other lines on the graph in the piano are also sine waves, which means that you could technically reconstruct all sounds by manually drawing out every single frequency with sine waves, but since sound moves a lot, this is hardly practical. The other thing is this: if there are a whole bunch of frequencies close together, how come the piano doesn't sound like a cluster of ugly notes? Well, in order to explain that, as well as the next waveform we're going to look at, the saw wave, let me quickly introduce you to this little unimportant thing we call the Harmonic Series. If the sine wave is like the origin, then the Harmonic Series is like physics or whatever. Well, it is physics, because you can probably refer every single bit of music theory back to this piece of shit. So you're going to have to accept this thing into your life whether you want it or not. Anyway, whenever you play 2 notes together, they're going to sound really nice, or not. But you'll notice that when you play 2 notes that are an octave apart, they will almost melt together, as if they were one. Really nice. Ah, no consonants. Well, because of physics, every frequency in the real world has a bunch of overtones or harmonics that sound like they belong to the sound. However, it turns out that if you keep multiplying this octave distance by going 3 times, 4 times, 5 times, etc., you will always get more and more of these consonant frequencies. This is where our friend the saw wave comes in. The saw wave is built out of a buttload of frequencies, but they all magically line up in this wonderful pattern that makes us all go, ah yes, this is good. This makes the saw wave one of the most harmonically dense waveforms. Here, let's add all of the harmonics of the saw wave one by one, and you can see the sine wave turn into a saw slowly as I add more frequencies. And it just so happens that this waveform, with all of the overtones in the Harmonic Series, looks like a saw. At least that makes the name easy to remember. Oh, another thing, this bottom frequency is the note that you're actually playing. We call this one the fundamental tone. It's kind of important that this one is the loudest of the bunch. Otherwise your head will think that you're playing another note, so your brain will pick out the loudest harmonic and assign it some kind of importance. Here, let me show you what happens when the 5th harmonic is the loudest one instead. See? It will no longer sound like a nice harmony, now it sounds like a bunch of dissonant notes playing together. So, this leaves us with a final important question. Why doesn't the piano sound like a convoluted mess? I mean, look at it, it's not as nice and organized as a saw wave. Well, as long as the other non-harmonic frequencies are a lot quieter and not very consistent like a sine wave, they'll just end up being a bunch of noise. And as it turns out, almost all the frequencies from a piano note fit inside the Harmonic Series. Here, let me subtract all of the frequencies belonging to the saw wave from the piano. This way we can hear all of the content in the piano sound that does not belong in the Harmonic Series. Well, it seems like there's not much left. This kind of explains why the piano sounds nice to listen to. All of the important frequencies in the piano sound belong to the Harmonic Series, which gives the note a form of coherence. Other sounds like clock tower bells or that sort of thing that don't really have a clear tonal center usually don't have their loudest frequencies organized according to the Harmonic Series. Alright, well with that out of the way, that just leaves us with two of the synthetic waveforms, the square wave and the triangle wave. The square wave is pretty simple to explain actually. It's just like the saw wave, but this time we skip one harmonic each time, creating the pattern you see here. It's called a square wave because of its chunky looks over at waveform land, but I think the harmonic makeup of a square is much more interesting. So, before we move on, let's tackle the triangle wave too. It's actually just like the square, skipping one of the harmonic series each time, but this time the harmonics become increasingly more quiet the higher up we go. So a triangle wave is kind of like a square wave's shy sister. Anyway, what is the main takeaway here? Well, the basic shapes didn't become so legendary because of their looks. In the end, I feel like they've cemented their position in synthesis, especially because of their harmonic makeup. Generally speaking, looking at the harmonic makeup of a sound can explain so much more about its timbre compared to just looking at the waveform, or guessing. The way a note sounds is determined by the way the harmonics move over time. So a guitar has a different harmonic makeup than a piano. Different harmonics playing in the harmonic series at different volumes. A G on a guitar will look slightly different than a G on a piano, but they are just different configurations of the same order of frequencies, with some noise in between. As long as the instrument is well tuned or decently sound designed, all of the harmonic information that isn't noise will most likely fall right into the harmonic series. This is actually pretty useful information to know, because now we know that the way harmonics move over time is a really good way to mentally visualize how sounds move. Although, it might be interesting to note that the square wave is the loudest of the bunch because it spends the most time at the top. More at the top equals more volume. Even though the saw wave has more harmonics, the square wave seems to be the louder one because of its shape. Of course, it's good to know both of these things, but whenever I'm working on music production, or when I'm making sounds, I always mentally visualize this frequency graph, because I think this is a really close visual representation of what sound sounds like. Until now, we've only talked about the way waveform related things show up in the spectrum. How about audio processes that deal with the audio signal as a waveform in a really obvious way? A really good example for this is actually distortion. Common clip distortion is known for chopping the top of a waveform off, shaping it into something new. So why don't we start doing that to a sine wave? Hey, that looks familiar. By chopping the top of the waveform off, we've managed to turn our sine wave into a square wave. But the most interesting part of this, that's the most useful to internalize, is to think about how the distortion affected the harmonics of our signal. So, you can see it's not perfect, but it's pretty close to a square wave. Alright. So what if we have a more interesting signal than a sine wave? What about two sine waves playing together? You can see that as I start distorting the signal, more and more frequencies are added on both of them, but they're also responding to each other. Whenever I'm designing sounds, I try to think about the way the sound moves inside the spectrum, rather than just taking it for granted as a process. Distortion can be used to add extra harmonics to signals, and filters can be used to remove them. But as a quick example, I can show you what a low-pass filter does. You probably already know, a low-pass filter will just remove the high frequencies from the signal starting from the top. What's interesting about this is the translation. So you notice how when I use the low-pass filter, yeah, duh, obviously it removed all of the high harmonics from my signal, but this also changed my waveform into something that looks closer to a sine wave. So the final takeaway that I want to give in this masterclass is to look at all the effects that you use and try to make this translation process in your head. So effects that only make sense in the waveform, try to see if you can predict what it's going to do in the spectrum. And for things that are obviously spectrum related, try to see if you can figure out what those things do to the waveform. Getting better at this translation process is, in my opinion, one of the most important aspects of getting better at sound design. If you're trying to get a certain sound, and you haven't quite figured out how to get it, maybe try to think about this. and you'll probably get closer than you were before.